Given a first-order language that consists of, as you know, three sets, the set of variables, the set of predicates, and the set of functions, we can start to formalize statements in predicate logic. This means that basically we can construct formulas by using, operators such as the conjunction or the implication and so on. What is special in predicate logic is that here, as the operands of those predicates, of those operators, we can use and we will use parameters with predicates with parameters, right? Like I can use a variable x as a parameter for predicate p or this constant as well, or I can even use, as you will see, functions with actual parameters as parameters for those predicates. These expressions are the smallest possible elements inside a formula, or as we call them, atoms. Now I'm going to define what an atom is. I mean, I will give the precise definition of an atom. Well, the atom definitely starts with a predicate, and then you can pass parameters to it, any number of parameters. Now I'm denoting those parameters with T1, T2, and Tn. Of course, formally, we have to specify that P is a predicate, so it's coming from the set of predicates, PR. This is one thing. The other thing is to specify how many actual parameters this predicate can take. This number should be correct, syntactically correct. Well, as you already learned, inside the set of PR, we give for each predicate the number of required parameters in superscript, sorry. So let's say this predicate P must take n parameters, where n is a natural number. This is why when I use the predicate, I must pass n actual parameters. Okay, and I also have to say something about what those parameters can in fact be. They can be, variables, constants, function calls, as you see up there, highlighted in red. So yeah, so this should be also part of this definition, that every Ti should be something special. And now I'm going to introduce a new concept that is called a term. So every Ti is a term. Now we only have to define what a term could be. This is exactly what I'm going to do. So I'm going to define what a term can be. I give the precise definition of a term. Well, first of all, term can be a variable, like up here, right? How to specify this? This is the first option. Well, of course, this can be easily formalized by the following. A term can be an x which is coming from the set of variables, right? That's it. So this means a term can be a variable. Also, as you can see here, a term can be a constant. How to formalize that? Well, as you know, a constant is coming from the set of functions. And you also know, I hope so, that constants are actually functions with 0 parameters. And of course, as you can see on the formula above, a term can be a function call with actual parameters. And this is why we are going to generalize this last line here. So this C could be not 0, but any number of parameters. And actually, let me just change the notation here. It can be a regular function with any number of parameters. So what can I do with such a function which is coming from the fn set? Well, of course, we can call this function. Let's call the function with the proper number of actual parameters, since f requires n parameter to pass. This function call must use n terms as parameters. So f, t1, t2, and so on, tn is also a term where f is a function with n required parameters. And of course, we have to say something about t1, t2, and tn in exactly the same way as we did it in the definition of an atom. Every ti is a term. So the function's parameters can be either variables, constants, function calls. Notice that I'm using the concept term inside the definition of a term. This is what we call a recursive definition. And this is dangerous because this, by applying those rules inside the definition, you might construct infinite terms. Therefore, we really must put additional constraint inside this definition, like apply those rules finite times, only finite times. It's not okay to generate infinite expressions, infinite terms. This would not be syntactically correct.